Right, in this video we're going to talk about Bessel functions. In fact, we're going to derive a series definition of these functions. Okay, now Bessel functions typically arise as solutions of problems involving circular symmetry. So if you get a, say, vibration problem or heat conduction problem in geometry involving circular symmetry, then typically when you solve the PDEs there, then you find these functions. So they arise in problems involving circular symmetry. Okay, we are going to derive them from the ODE, which is called the Bessel ODE. So these functions satisfy the following ODE. So got t squared y double prime plus ty prime plus t squared minus nu squared y equal to 0. I'm going to call this ODE equation number 1. So for this ODE, we're going to look for a series solution of the following form using the theory of Frobenius. Okay, we're going to look for a solution of the form y equal to summation of ak t to the power nu plus k. K runs from 0 to infinity. Now if we differentiate this, we are going to have the following. So differentiating these ones will give us a nu plus k into a k t to the power nu plus k minus 1. Still k goes from 0 to infinity. Then the second order derivative going to be the summation of nu plus k times nu plus k minus 1 ak t to the power nu plus k minus 2. Okay, then we are going to substitute into the ODE equation number 1. So substitute into this equation. So in this equation we've got t squared times y double prime. So that t squared is going to multiply this term. Then we're going to get the following situation after a bit of rearranging. So the first term is just going to be this coefficient times ak. So we're going to have nu plus k minus 1. Then for the second term, if you multiply this by t, then you're just going to have nu plus k ak, and then for this last term here, so that one is going to give us minus nu squared. So minus nu squared, and then everything here is multiplied by ak times t to the power nu plus k, and then there is one more term here, which is t squared times y So that term is going to give us the summation of ak t to the power nu plus k plus 2, and then we're going to have 0 on the other side. Now, the first thing we're going to need to do here is to make sure that the powers of t are the same. So see, this one has got plus 2. So what we're going to do is we're going to let k plus 2 be a new dummy variable. So if you let k plus 2 be L, for instance, so L is k plus 2, then what's going to happen is when k is equal to 0 here, L is going to be equal to 2. Then k is L minus 2. So it's going to be A of L minus 2. That's going to be t to the power nu plus L. Okay, but L is a dummy variable, so that means we can simply replace it by k again. So when we do that, then our ODE, or our equation, is going to look as follows. I'm just going to rewrite this second term here. So basically this second term is just going to be summation of ak minus 2t to the power nu plus k, summing from 2 to infinity. Now the next thing is to make sure that the lower summation indices of these two terms are the same. So that means we're going to evaluate this one at 0 and also evaluate it at 1. Okay, and then the two of them, then we can combine. So when we do that, so in the next line, when you plug in k is 0 there, this is what we're going to get. So we're going to get nu into nu minus 1, and then the second term is just going to be nu, and the last term is going to be nu squared. It's going to be times a naught. And then when k is 1, we are going to get nu plus 1 times nu, and then the middle term is going to be nu plus 1, and then minus nu squared. This is going to be times a1 times t, and then close brackets. So maybe it's best to bring this term here. So we're going to have nu plus 1 times nu, and then the middle term is going to be nu plus 1. The last term is still going to be nu, then a1t. Okay, then everything here is multiplied by t to the power nu. So what we're saying is that when k is equal to 0, it's going to be nu times nu minus 1, which is this term here. This one is just going to be nu, and that's going to be nu squared. So nu and nu squared. Then when k is 1, it's going to be nu plus 1. This is going to be nu, which is this term here. And the middle term is going to be nu plus 1. That one is still going to be minus nu squared. And then after that, what remains are two summations that both have got a lower summation of k equal to 2, and so we can combine the two summations, and they are going to look like this. So we're going to have nu plus k here times nu plus k minus nu squared. We're going to explain this in a moment. Then there's going to be a k minus 2 from the second term, and this is times t to the power nu plus k equal to 0. So let's just explain what's happening here. So if we factorize nu plus k here, so you got nu plus k and nu plus k there. So we're going to have nu plus k into, then this is going to be nu plus k minus 1 plus 1. So that's why it's going to be nu plus k times nu plus k, and then minus nu squared. And then this, you can notice now this is a difference of two squares. So I got nu plus k minus nu squared. If you factorize that, because it's a difference of two squares, it's going to be nu plus k minus nu, and then nu plus k plus nu. This one is just k, and this one is 2 nu plus k. So that's what this is now going to simplify to in the next step. And then this one, we've got nu squared minus nu squared here, got minus nu plus nu. So this first term is just going to vanish, and then this term here is going to simplify to nu plus 1. Again, the nu squared terms cancel out, then you got nu plus nu here, and then plus 1. So so simplifying is going to give the following situation. So we're going to have a1 2 nu plus 1 times t to the power 1 plus nu times the summation from k equals to infinity of k into 2 nu plus k ak. Then this is going to be plus ak minus 2 t to the power nu plus k equal to 0. Then from this we can see that we're going to have a1 2 nu plus 1 equal to 0. So this is telling us that so long as 2 nu plus 1 is not equal to 0, then a1 is just going to be equal to 0. And then similarly, this term is going to be equal to 0. So if we solve for ak from there, we're going to have ak equal to negative a k minus 2 all divided by k 2 nu plus k. This is for k equal to 2, 3, and so on. So if we plug in k equals to 2, for instance, so this gives us a2 is minus a0 all over 2 times 2 nu plus 2. So this we can write as negative a0 all over 2 times 2 into nu plus 1. Let's just do one more term. So a4 is going to be minus a2 all over 4, k is 4. Then this is going to be 2 nu plus 4. But then if we plug in a2, this is going to be minus 1 over 4. We can factorize 2 here. So it's going to be nu plus 2. And then a0, so a2 is minus a0 over 2 times 2 nu plus 1. And then if we tidy things up here, we can write this as a naught over 2 to the power 4 times 2 factorial nu plus 2 nu plus 1. Okay, so it's going to be a 4. And then if we keep going with this, then we are going to see that in general a to m is going to be negative 1 to the power m times a naught. Then in the denominator, we're going to have 2 to the power 2m, which is like this term here. Then we're going to have m factorial, just like this term. And then we're going to have nu plus m minus 1 all the way down to nu plus 1. Okay. Now, this term we can write down in a closed form or in a more compact form by doing the following. If we multiply both numerator and denominator by nu factorial, you can see that if you go down from here to nu times nu minus 1 all the way to 1, then that whole thing is going to be nu plus m factorial. So what we're going to do is we are going to multiply the denominator by nu factorial and also multiply the numerator by nu factorial. Something else that we're going to do that you're going to see its usefulness as we keep going. Multiply both numerator by 2 to the power nu. Then what's going to happen is our numerator is going to be negative 1 to the power m a naught 2 to the power nu gamma of nu plus 1, which is nu factorial. Then in the denominator, we're going to have 2 to the power nu plus 2m. And we're going to have m factorial, which is this term. And the last term is going to be m plus nu factorial, which is the gamma of nu plus m plus 1. Now, remember that a naught is arbitrary. So because a naught is arbitrary, we can choose it at will. So we're going to choose a naught to be equal to 1 over 2 to the power nu times gamma of nu plus 1. Then it's going to cancel off those two terms. So our a to m simply becomes negative 1 to the power m, all divided by 2 to the power nu plus 2m times m factorial times gamma of nu plus m plus 1. So then our solution, so y of t, remember this is the coefficient of t to the power nu plus k here, okay? So our solution y of t is going to be expressed as follows. So this is going to be summation from m equal to 0 to infinity, negative 1 to the power m, all divided by m factorial times gamma of nu plus m plus 1 t over 2 all to the power nu plus 2m. This is denoted j nu of t, where j nu of t is the Bessel function of the first kind. J nu of t is the Bessel function of the first kind of order nu, so this function is regular at the origin. There is a second solution which is singular at the origin, and it's called the Bessel function of the second kind. So that one is denoted y nu of t. It is defined as the cosine of pi nu times j nu minus j minus nu, all divided by sine nu pi. So then the general solution of the ODE 1 is given as follows. So the general solution y of t is going to be a times the Bessel function of the first kind plus b times the Bessel function of the second kind, where a and b are arbitrary constants. So yeah, so this derives the series definition of the Bessel function. So the main aim of this video was to demonstrate this derivation here, which we are going to use subsequently to study properties of the Bessel function. Thanks for watching the video. Please do subscribe to support our channel.